7, 7, 7, right? Oh, I can't do math. Rather, 1, 2, 3. And what do I get? 8, 10, 12, and 7, 7, 7. Okay, so take the identity matrix. Do the same row operation to it. What do you get? All right, let me call this thing E2. This is a type 2 example we're doing right now. So what happens if we look at 1, 0, 0, 0, 2, 0, 0, 0, 1 times our matrix? 1, 2, 3, 4, 5, 6, 7, 7, 7, 7. I mean, you can work it out, right? We get 1, 0, 0. Oh, I'm sorry, I can't do math. 1, 8, 7. Anyway, you get 1, 2, 3, and 8, 10, 12, 7, 7, 7. So we can also do row scalings just the same way, right? What was the last kind of row operation we talked about? Type 3, right? So we do something like, so yeah, let's say, what do you want to do? Row what? Row 1 plus row 3. I'll do plus 2 row 3 there. We'll make it. We'll really get row 1 plus 2 row 3. Oh, why did I do that? 14 plus 1, 15. 14 plus 2, 16. 14 plus 3, 17. The other rows are unchanged, 4, 5, 6, 7, 7, 7. All right. So I take the identity matrix, and I do row 1 plus 2 row 3 to it, right? That gives me 1, 0, 2, 0, 1, 0, 0, 0, 1. All right, so this is what I'll call E3 for the sake of discussion. And guess what? This is equal to E3 times A. We can try. Here, I'll do it down here. So I get 1. Oh, I can't do math. Let's see here. 1. Oh, we have 15. Yeah. 4, 7, 2 plus 4, 16, 5, 7, 17, 6, 7, yeah. So as is usually the story in here, I've showed you for a 3 by 3, right? So it must be general. I'm sorry?
So what you said you found it in the book. What did you call it again? You define it as something.
Oh, this is a so-called counter-diagonal matrix. So like, for example, the 4 by 4 counter-diagonal would be what? But I think that terminology would still also allow for like 2, 3, 7. That would also be counter-diagonal. No.
So the identity matrix is also the element matrix? Is that what you're saying?
The identity matrix is, which row operation would that correspond to? I don't know. Is multiplication by 1 a row operation? If you allow that, sure. If you don't, I don't know.
I just wanted to know what you specifically meant by elementary matrix.
An elementary matrix is one which we obtain by taking the identity matrix and performing either a type 1, type 2, or type 3 row operation too. So it turns out every last one of those is invertible. All elementary matrices are invertible. And the inverse of an elementary matrix is another elementary matrix of the same type, which is kind of fun because, well, I mean, what do you think the inverse of, what's the inverse of, like this matrix, what's its inverse? How do you undo a row swap? What's your name? Madison, what's your name? Eric, you're Madison. Madison, you're Eric. How do we undo this? We just switch your names again, right? One more time. So it's the same. Sorry, it was just too disturbing. Sorry. I don't know. Surely there's some girl named Eric somewhere, right? I mean, Erica. I don't know. I mean, I saw Jennifer referred to in a male sense in a newspaper ad once. So like, I think you can't underestimate the stupidity of parents somewhere.
What are you gonna name your kid?
Oh, that's a good question. Yeah, Benjamin. I know it doesn't. Yeah, HDMI is what I have so far. Hannah, Daniel, Matthew, Isaac, which was not on purpose. That's not chronological either. But I don't know, the B doesn't really fit, but yeah, he's Benjamin. Yeah.
It's a B type.
5, but soon 5. But this week, hopefully, yes. I know, it's shocking that I'm married, but in fact, this is its own inverse. If you multiply this matrix by itself, you get back the identity matrix. You can check that E squared is the identity matrix. It's its own inverse. So row swaps are their own inverse. To undo multiplication by 2, you do multiplication by half. To undo this one, instead of adding to row 3, you subtract to row 3 to row 1. So the inverse of each elementary matrix is another elementary matrix of the same type, in fact. But yeah.
Did you add elementary matrices? You know, like do a row swap and a multiplication at the same
Can I add elementary matrices? That I
Not add, but like use them to do 2 operations at the same time, like a row swap and.
Very, very, very good question. So in fact, if we look at the reduced row echelon form of A, what it's going to be is EK minus 1, E2 times E1 times A, where these are the elementary matrices corresponding to the K row operations that achieve the Gauss-Jordan elimination. So what that means is there's a formula which relates the reduced row echelon form of A to a product of elementary matrices times A. And that I will use to prove things in here. I will prove a few small things in here, most notably the linear correspondence with this. So thank you for that question. It makes this 10 minutes better. I don't really have much more to say about elementary matrices in here. We need them for proving the linear correspondence, and also there's something called the LU decomposition. I feel like we really should cover the LU decomposition. It seems wrong to not cover the LU decomposition here, right? But sorry, it's awful. But yeah. Anyway, I shut up, you guys. Have a good weekend. And so Tuesday I should be here, hopefully, and then Thursday Dr. Smith will talk about the project, which I will at some point post soon. And I will give you guys a little bit longer than his class because his class has had the project to fiddle with for a while now. And you will first hear about it next Thursday. But I will post it before then, hopefully tonight if I remember.